It's very odd, but interesting nonetheless. All right. So just looking at the HOMO orbitals here, or HOMO geometries and orbitals, you can see here that we have the octethal porphyrin. We're looking right down the porphyrin plane. Right down here we have our phenol. You can see a little hydrogen here. And as you can see, most of the HOMO intensity or electron affinity is in this, right around this iron metal, and it looks very much like a D-based orbital with the 4 lobes. So as you can see here, it's fairly clear what's going on. There's a little bit here on the ligands as well, and a little bit out here on the ring, but it's basically all centered on the metal, which we can see here is very similar when we have the phenoxide. So you can see here that that proton is gone, so we have the phenoxide. There's a little bit more centered on this oxygen here than compared to before, but overall it's pretty much all based on the metal. One thing of note here, as you can see here, the ring isn't as flat in this model. It has a little bit of a ripple in it, which is an interesting thing to look at, because in some proteins it does have that same different ripples in it, or different tilts and bends, and that needs to be explored further in our protein-based research. So this might be a good way of looking at what is going on in those systems. And here's where things get really funky. So when I put the tyrosine on, the tyrosine fell off. And so we can see here that most of the electron density is on this tyrosine ligand. So you can see it's coming out here. Here's the carbonyl side. Here's the amino side of the amino acid. Then here's where it should be ligating to the metal. So what I'm thinking happened is there was just too much weight or too much mass, reduced mass, that the oxygen bond wasn't strong enough to hold it together. And it does make sense. In proteins, it's not just that one oxygen bond that's holding it on. It's a whole bunch of interactions all the way around the ring that's holding it together. So it's it does have some merit. So with that, I'm going to give you some conclusions. First one is you want to use swell ligands. Obviously, the tyrosine fell off. It was pi stacking with the ring. Obviously, that's not what we wanted to look at. We wanted to look at what happens when we have ligands on there. So that's why the tyrosine ligand had such a large effect. And what we need to do is we need to use smaller ligands without the whole amino acid backbone on there. Otherwise, they won't give us results that we're looking for. So it seems to be a fairly effective way. There's a whole bunch of papers out there on DFT with these porphyrin rings, where they are looking at different ligands, different substituents, that sort of thing, and they have used it to draw correlations to proteins. It doesn't seem to be very effective for generation of observable spectrum, but I know I've read several papers where they have generated vibrational spectra, and they match fairly nicely with published experimental results. So there's one thing that we can use, but the absorbance spectra don't seem to be as useful, or obviously I did it incorrectly. Overall, the spin polarized unrestricted DFT does a fairly good job of calculating for iron porphyrins. With that, any questions?
Okay, thank you, Seth.